In this lecture, we will discuss the class equation with some applications and then proceed towards proving the G-Bazar theorem. The class equation of a group G is given by order of G is equal to order of center of G plus summation over A not in the center of G, order of G upon order of N of A. This equation is known as the class equation of G. For example, if we choose G as a non-abelian group Q4, the group of quaternions, whose elements are given by 1, minus 1, I, minus I, J, minus J, K, and minus K, with the properties that I square is equal to J square is equal to K square is equal to minus 1, Ij is equal to Jk is equal to Ki, Ij is equal to K, Jk is equal to I, and Ki is equal to J. And similarly, Ji is equal to minus K, Kj is equal to minus I, and Ik is equal to minus J. So this is the group of quaternions. Now we discuss the class equation of Q4. For this, we will compute the normalizers of some element A. So here, first we choose the normalizer. First, we will discuss about the center of Q4. The center of Q4 is the set of elements that commutes with all the elements of Q4. And this can obviously seen to be the set of two elements, 1 and minus 1. Now once we have an element in the center of a group, the normalizer of that element is the whole group. So this means that normalizer of 1 is equal to Q4 and normalizer of minus 1 is also equal to Q4. Now we discuss the normalizer of the rest of the 6 elements of Q4. So first we compute the normalizer of I. And in fact, by the definition of normalizer, it is the set of those elements of Q4 that commutes with all the elements of Q4. That commutes with I. So normalizer of I is the set of those elements of Q4 that commutes with I. So therefore, we can see that now since the elements from the center of a group commute with all the elements, so therefore 1 and minus 1 commutes with I. So therefore, normalizer of I contains 1 and the normalizer of I also contains minus 1. Then similarly, we can see that I will commute with I and minus I will also commute with I. And from the definition of the Q4, we can see that I does not commute with J and I does not commute with K. So therefore, the normalizer of I is the set of 4 elements, 1, minus 1, I, and minus Y. Similarly, the normalizer of J will be the set of elements 1, minus 1, J, minus J. And similarly, we can see the normalizer of K is the set of elements 1, minus 1, K, and minus K. Thus, the class equation of Q4 is order of Q4, which is equal to 8, is equal to G upon normalizer of 1, order of G upon order of normalizer of 1, plus order of G upon order of normalizer of minus 1, plus order of G upon order of normalizer of I plus order of G upon order of normalizer of J plus order of G upon order of normalizer of K. And in fact, we can see that the normalizer of minus I will be same as normalizer of I and so on. So that is, we have 8 is equal to 1 plus 1 plus. Now all of these is 2. 2 plus 2 plus 2. And this is the class equation of Q4. Now we will proceed towards having some applications of the class equation. Or before doing that, we will make one more conclusion here, or we will make one more remark here. Remark: if G is abelian, then class equation of G is order of G is equal to 1 plus 1 plus 1 plus so on. And this one has to be taken as order of G times. Because whenever we have an abelian group, then the normalizer of every element will be the whole group. So this means that the order of G will be equal to order of G upon normalizer of identity plus order of G upon normalizer of some different element and so on. But every element will have its normalizer equal to the whole group. So the class equation of an abelian group is always of this form. And whenever we have a non-abelian group, then the class equation will always have at least one entry that is greater than 1. Now we make some applications of class equation here. So this theorem is actually one of the applications of class equation. If G is a group of order p power n, then order of center of G is greater than 1. And this can be, in other words, we can say that whenever we have a group of order p power n, then the center of G is always a non-trivial subgroup. And we can prove this theorem using the class equation. First, if n is equal to 1, then order of G is equal to p, and so G is cyclic. Because every group of prime order is cyclic, thus order of center of G in this case will be equal to p, and this is greater than 1. Now suppose if n is greater than 1, then consider the class equation of G. So in this case we have order of G is equal to order of center of G plus summation A does not belong to the center of G, order of G upon order of normalizer of E. Now this is the class equation of G. Now here order of G is equal to p power n, and we are assuming that n is greater than 1. Also, if A does not belong to the center of G, then order of normalizer of A order of normalizer of A will be equal to, so when actually A is not in the center of G, then order of, then actually we have normalizer of A, then normalizer of A is not equal to G. So in fact, in this case, the normalizer of A will be a proper subgroup of G. In fact, N of A is a proper subgroup of G. Thus, order of N of A will be equal to some P power M, where this M is less than N. Because we know that the normalizer of every element is a subgroup of G, therefore in this case normalizer of A will be a proper subgroup of G, because we are assuming A is not in the center of G, and using the result that whenever there is an element which is not in the center, the normalizer of A will not be equal to the whole group G. So therefore in this case we conclude that normalizer of A is equal to P power M, where M is less than N. So thus order of G upon order of normalizer of A will be equal to P power N minus M. So when M is less than N, where N minus M is greater than or equal to 1. So thus, let's name this equation as first. Thus we have from first. Now since we can see that P divides order of G, and now since order of G divided by order of N of A is equal to P power N minus M, where N minus M is greater or equal to 1. So this means that P also divides this term. So therefore, from equation first, whenever we have these two terms divisible by P, P is dividing order of G and P is also dividing this term. So this implies P divides order of G. So therefore, from equation number first, we have P divides order of center of G. Because P divides order of G and P also divides order of G upon order of N of E. So thus, whenever we have a prime number dividing order of G, this means that order of center of G is not equal to 1, that is Z of G is non-trivial. So this is what we needed to prove, that the order of center of G is greater than 1. So now since we have proved that order of center of G is not equal to 1, this means that order of center of G is greater than 1. So this was one of the applications of the class equation. So whenever we have a group of the form whose order is of the form P power N, then the order of that group will always be greater or equal to 2. In fact, it will always be a non-trivial center. Now, we prove one more result here that's called a G by Z theorem. In fact, that will also be useful in proving something about the groups of the form P power N. But before going into the G by Z theorem, we shall make one definition here. Definition: P group. A group whose order is of the form P power N is called a P group. So once we have the definition of a P group, we can state the previous result as, the previous result can thus be stated as that every P group has a non-trivial center. So the statement of the previous theorem. Previous theorem restated. the center of a non the center of a P group is always non-trivial. So whenever we have a P group, its center is always non-trivial. Now we proceed towards proving the G-Bazar theorem. Actually, that will also be useful in proving some results about the P groups. So we have a theorem here that's called G-Bazar theorem. Now here in this theorem, the Z denotes the center of G. If Z of G denotes the center of a group G, then if G upon Z is cyclic, then G is abelian. This is the statement of G by Z theorem, that if Z is the center of a group G and such that G by Z is cyclic, then G is always abelian. Now we proceed towards proving this result, and this result can be proved by just using the thing that whenever we have a cyclic group, it will be generated by a single element. So let G by Z is cyclic, and let G by Z be generated by an element Gz. So there will be an element in G by Z which generates the whole group G by Z, and let that element be Gz. Now let A and B be the elements of G, then there exist integers I and j, such that A is equal to, or we can write now, since A Z or AZ and BZ will be the elements of G by Z. Now this AZ is an element of G by Z, so this AZ will be equal to GZ power I. So this AZ is equal to GZ power I, and similarly this BZ will be equal to GZ power G. Now by using the properties of the cosets, this can be written as G power I into Z, and this can be written as G power J into Z. So therefore AZ is equal to G power I into Z, and BZ is equal to G power J into Z. We are actually in a process to show that the group G is abelian. Now since we have chosen two elements A and B from the group G, we will prove that AB is equal to BA. So now thus, so once we have AZ is equal to G power I into Z and BZ is equal to G power J into Z, this implies thus there are elements X and Y in center of G such that A is equal to G power Ix and B is equal to G power J into Y. because this is obtained from here that AZ is equal to G power I into Z and BZ is equal to G power J into Z. So this means that A is equal to G power I into X for some X in the center of G, and B is equal to G power J into Y for some Y in the center of G. Then A into B, this is equal to G power I into X, then B is equal to G power J into Y. Then this can be written as G power I into X, G power J into Y, and this is done by the associative property of G. And here this element X belongs to the center of G, and G is an element that belongs to G. Now this is equal to G power I into, this can be written as G power J into X into Y, because this X is in the center of G and therefore it commutes with all the elements of G. Now further this can be written as, again using the associative property here, or G power I and G power J. This is equal to G power I plus J into XY. Now this can also be written as G power J plus I. And doing I plus J or writing J plus I, this is just using the commutative property of the set of real numbers. Now X, Y are both in the center of G, so instead of XY we can write YX easily here. Then this is equal to, now again using the distributive property here, this is G power J into G power I into Y into X. Now this again using the associative property of the group. Now since Y belongs to the center of G, therefore we can commute G power I and Y. So this is G power J, then write Y, G power I, then X. Now again using the associative property, we can write this is G power J into Y, then G power I into X. Now since G power J into Y is equal to B and G power I into X is equal to, so therefore we have proved that AB is equal to BA, thus G is abelian. So therefore whenever we have a group G such that G upon center of G is cyclic, then G must be an abelian group. So we have some remarks here. So this statement actually shows that this theorem actually shows that G upon Z must be non-trivial, must be trivial. Because whenever because this theorem states that G upon Z is cyclic, then G is abelian. But once G is abelian, then G upon Z must always be trivial. Now we proceed towards one more application of the class equation, or the application of this G by Z theorem. And in that theorem, we will prove something for the P groups. The theorem is like this. If order of G is equal to P square for some prime P, for some prime integer P, then G is abelian. In fact, we will also show that, and in this case, either G is isomorphic to ZP square, or G is isomorphic to ZP cross ZP. So we will also show that there are only two non-trivial groups of order P square, both of which are abelian. One of them is cyclic and the other is isomorphic to ZP cross ZP. So we make the proof like this. So using the theorem about P groups that states that every P group has a non-trivial center. Thus, clearly, order of center of G is equal to P or P squared. Because here order of G is equal to P squared, therefore G is a P group, and every P group has a non-trivial center, therefore order of center of G is equal to P or P squared. Now, if order of center of G is equal to P squared, then G is abelian. And second, and if order of center of G is equal to P, then order of G upon center of G is also equal to B, because center of G is always a normal subgroup of G. So this implies G upon Z is cyclic. Thus, G is again abelian. So therefore, either center of G, whether center of G is equal to P squared, then G must be abelian, or if order of center of G is equal to P, then G is again. So this was the proof that whenever we have a group of order P squared, then it must be an abelian group. Now we will prove that this group of order P squared is either ZP squared or it is ZP cross ZP. So now if G has an element, if G has an element of order P squared, say order of A is equal to P squared where A belongs to G, then G is cyclic. Then G is cyclic and is generated by A. And is generated by A. Thus, in this case, G is generated by an element of order P square, and therefore G is isomorphic to ZP square. Now, by Lagrange's theorem, the other case is that the order of every element of A should be either equal to 1 or it should be equal to P. But since only the identity element has order 1, therefore when G does not have an element of order P square, then every non-identity element of G must have order equal to P. So the other case is, thus assume every non-identity element of G has order equal to P. Then we define a mapping. Define a mapping suppose psi from ZP cross ZP into G by psi of x power A y power B is equal to x power A into y power B. Then this mapping is an isomorphism. Then this mapping is an isomorphism. So for showing that this mapping is an isomorphism, we need to show that the mapping is well defined and it is also 1-1 as well as onto. To show psi is well defined. Let x power a, y power b is equal to x power c, y power d. Then this clearly implies x power a is equal to y power b. So this implies x power a is equal to x power c, and y power b is equal to y power d. Then this clearly implies x power a into y power b is equal to x power c into y power d. And this implies psi of x power a y power b is equal to psi of x power c y power d. So this means that the mapping is well defined. Now reversing the order of steps here, we can see that the mapping is 1, 1. So this implies the mapping is well defined, and in fact reversing the steps here, we see psi is 1. Now since the psi is a mapping between two finite sets, and once we have a 1-1 mapping between two finite sets, then that mapping must be onto also. So thus this implies psi is also onto. Thus psi is an isomorphism. Thus, and in fact it can also be seen that the psi is a homomorphism. Thus psi and psi is also a homomorphism. So thus psi is an isomorphism. So therefore G is isomorphic to ZP cross ZP. So therefore we conclude here that every group of order p square is abelian, and there are exactly two groups of order p square. One of them is cyclic, which is isomorphic to ZP square, and the other one is abelian and is isomorphic to ZP cross ZP. So with this thing, we stop this lecture here.